So Nino, can you hear me? Yeah, okay, works. Now, all right, the first thing we want to do is protons, neutrons, and electrons, all that stuff to do with the makeup of an atom. And this is true even with the new Bohr model of the atom that we just talked about today. So if you have just a regular atom like this, we've got these things in the middle. These things are positive, those are called protons. The neutral ones are neutrons. And then we've got the little electrons around the outside. I'm going to draw right now the new model of the atom that we just found out about today.
Do we need to know like plum pudding and like...
Yeah, we do. But this right here is the Bohr model. Okay? Now let's put another electron over here. We don't know why I'm putting this in another shell yet. We'll learn about that more when we talk about the next unit, periodic table. But these are the electrons around the outside over here. So for this atom right here, we've got 1, 2, 3 protons. So 3 protons. We've got 3 neutrons. And we've got 3 electrons. Okay? Just from this information by itself, we can determine which element this single atom is. We can look at this information right here, and you can tell me which one it is. You look at that, the protons. The protons tell you which element it is. So this one just happens to be 3, would be lithium. So lithium is the element. This also has 3 neutrons. So its atomic mass, or its mass number, I'm sorry.
Yeah.
Yes, that's right. Its atomic mass is going to be 6, right?
Yeah.
I think so. And this is the number of protons. Now its overall charge, what's its overall charge here? 0. It's 0 because you have 3 protons and 3 electrons. Those two cancel each other out.
Wait, when you try to find the number of protons, you subtract electrons from neutrons?
When you try to find the charge, you can think of it this way. The charge is the protons minus the electrons. So it's the number of protons minus the number of electrons. So in this case, it's 3 minus 3, which is 0. The overall charge is 0. It's neutral. But what if we had 4 electrons? We had another electron on the outside over here. Oh my God! What do we do now? We've got 1 extra electron, so the overall charge is now going to be minus 1, right? And if we have like, let's keep that as 3, but let's keep this at, now let's move this to an incredibly large number. This would never happen, but we can still solve it. 12! Holy crap! What charge is this going to be now? Negative 9, that's right. So no matter what kind of problem I can throw at you, you can always figure that out. Now, some weird problems I might ask are things like, if I give you the overall mass, the atomic mass, let's say it's like 52, the overall mass, the mass number of the atom, is 1 single atomic mass, and let's say that you have like, I don't know, the number of electrons are, let's say that it's, I don't know, let's say 20, and the charge is, well, you can figure that out, and you can also figure out,
You can't figure out the charge.
let's do this. Let's do the charge. If you can figure it out for this, let's say the protons, the number of protons is 30, what would that be, 32.
So now the charge is 12.
12.
So the charge would be 12. How many neutrons does it have?
How do you know that?
20.
20, good.
Why?
How do you know that?
Because the atomic
protons,
mass is 52
yeah.
and we have 32 protons.
Right, the overall mass of this atom is 52. That's the protons and the neutrons together. So since we have 32 protons already, we must need 20 more neutrons to get there to 52. That's the overall mass. Okay, good.
What? No.
Protons plus neutrons.
This isn't that easy.
Yeah,
It's mad easy.
Oops, I moved it. I moved the camera.
Yeah, that's where I can take out boxes like this, right? What if I do that?
Are you touching my...
You can figure that out, right? From the information right now. What if I take out this? I can do that. I can still take that out. You can still figure that out right now.
I can't see anything this close. Can I move that?
Careful. Excuse me?
Uh,
No, I'm ignoring that right now. Yeah, I'm ignoring it. I'm just asking a different question. Sorry. Okay?
I can't see either because of your head. Can I go back?
You can't see because of my head?
Yeah, because when you're writing, you're in my way.
Alright, yes, that's fine. Oh, I need to step away from this, yeah. So you got 20, 32, blank and blank. You can figure this out. You can deduce this. These added together, that gives you the overall mass. And since you know the charge is plus 12, that means there must be 20 electrons.
20.
Yeah,
Okay.
so you can figure all that stuff out.
Is that better?
It's good.
Wait, who's
All
recording
right.
this for?
That's it for protons, neutrons, and electrons. Pow. Half-lives. Let's do half-lives.
Oh, I haven't done this.
Is it recording? Yeah, it's still recording. We've done 5 minutes. That was a good 5 minutes. Let's keep on going. 5 minutes. The main equation for half-lives. Let's talk about that. That thing is going to be key.
Wait.
There's different ways you're going to ask questions related to this. Yeah?
Do we need to know like the rules to like an atom?
What do you mean?
Like it's an electron's like it's smaller than an atom. It fits into.
Oh yeah. Like that argument.
Uh-huh.
Yeah, you definitely need to know that. So what are they?
Well, it's talking about electrons, right? So electrons are smaller, are tiny.
Yeah.
They fit into an atom,
Mhm.
and they're negatively charged.
They're negatively charged and they're smaller than atoms.
Yeah.
And what else do we know? We know that overall atoms are neutral.
Yeah.
So therefore, according to Thomson, this is Thomson's plum pudding model here.
Yeah.
Therefore, electrons must be inside atoms, and they must have some other. There must be some other positive stuff inside an atom to balance out those negative charges.
All right.
Right. That's it. That's what you need to know.
Okay.
Okay.
Hmm.
And what disproved? This is a good question. What disproved that model of the atom? That plum pudding model of the atom? What is the thing that disproved it? Yeah.
When they were shooting those things through the foil and they hit when they hit the center down, so.
Do we need to know like?
That's right.
Do we need to know like who Thomson is and like? I
You
mean,
need to know it enough to answer a good multiple choice question.
Wait, what were they shooting through?
They were shooting through gold foil.
What?
and who is?
Oh, they're shooting helium atoms, or also known as alpha particles.
Oh yeah, right.
Oh yeah, alpha. We'll talk about that soon. Okay. What else? I think that's about it for the history.
And wait, what's the guy who changed
Rutherford.
Rutherford?
You need to know J.J.
What's
Thomson
his first name?
and Ernest Rutherford. And the last guy we just talked about is Niels Bohr. So those three guys are important. That's why it's called a Bohr model, yeah.
What's the point of knowing that?
You need to know.
The last names, you'll recognize it. I won't say what is the first name of Rutherford.
Ernest.
What's the middle name of Rutherford? What is the middle name of Rutherford's dog? No, I won't ask you that sort of thing.
Alexander.
That's right.
I just spelled boys.
How'd you know?
Okay. It's getting kind of dark in here. All right, let's go on. So the next thing on here is half-lives. The main equation for half-lives is, you know this. We don't know this.
Oh wait,
It's the initial amount
initial amount times 0.5
times 0.5
to
raised
to
the
number of
number of
half-lives.
half-lives. And that equals
The
remaining.
remaining.
Now, this is for honors. For general, you guys don't need to memorize this. But for honors, you do. Crazy. It's getting kind of dark. Should we turn on the lights?
Terrible trend.
I think we should.
Does that say initial amount times 0.5?
Wow! Okay. Initial amount times 0.5 raised to the number of half-lives. That equals the remaining amount. Okay? This is the overall equation for half-lives. We derived it ourselves in class. It comes from the basic idea that every time you pass a half-life, half of the stuff is taken away. Okay? Or decays. So you start off with the initial amount of stuff. That's 100%. It's radioactive. Then you go through one half-life, and then how much is left? 50. That's right. 50%. Then you go through another half-life. Yes, now 25% is left. You keep on having it.
12.5.
So the definition is important here. Half-life is the amount of time it takes for a substance to decay in half. Right?
You need to know that. That's a trick question.
Of course you need to know that. You should have that just like you should know that by memory. You should be thinking that when you go to sleep.
Wait, so the half-life is the amount
really.
of time.
I know like what happened.
But the amount of time.
You'll need to know this in order to figure out what the question is asking.
So just like know what it is. Not like
Know what it is, so that way when I ask you a question about it, you'll know what to look for.
Okay.
That's the trickiest part of half-life problems, is just figuring out what the question is asking you. So once you figure out what the question is asking for, it becomes a breeze. It's very easy. The key to understanding what the question is asking you is to know the definition. Half-life just means the amount of time it takes for half the stuff to go away, to decay. That's it. All right? Now, if we use this equation, it's a very powerful equation, because now we can give any amount of time to you guys, and we can say it has a half-life of blah, 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 and you can tell me how much is left. Or you can tell me how much we started with. It's pretty cool. So let me give you an easy or kind of a medium-sized question for that. Let's say that, for example, you start off with 21, I'm making this up right now, 21.5 grams of radioactive stuff. I could make up an element right now, but I don't need to. It doesn't matter. That might be something that would throw you off. So it doesn't matter which element it is for these radioactive problems. It does not matter for these half-life problems, I should say. So we start off with that much. That's our initial. Let's say the half-life for this particular thing is 50.92 seconds. Right? And we know that the substance is so many seconds old. So the question is, how much is remaining after, let's say, I'm going to make this easy, so let's say 225.3 seconds. I could convert that into minutes if I wanted to, but I chose not to, just to make it easier. So how much is remaining after that many seconds? So you have to think about what's given to you in this question.
I know how to do it.
Okay, so you think about what's given to you. This is the initial stuff. That's the initial amount. We know that the half-life is this many seconds. And we know that this stuff has been around for that many seconds.
So we have
So
to.
that much time has passed, and that's how much one half-life is. So you should be thinking right now, you should be thinking about, yes, the number of half-lives
So we
that have
divide-
passed. So you can put that into that equation right
So we
there.
divide
So this is what we do. Let's just do it.
5.3
right now.
divided by
Can I go on this side? Yeah, that's how it works.
50 point.
This is going to be a little bit cramped because I got to fit it on the screen.
4.43.
Okay, let me just do it all out right here.
Who's this video?
So we've got 225.3
Puts it on the website.
seconds, parentheses,
over
1 half-life over 50.92 seconds. Now, if this was in minutes, we'd have to convert that to seconds first.
Wait, why can't
Wait, there's
when
4
we start working on
seconds.
your tests, can we just do 225.3 divided by 50?
Show this whole thing. That will keep you on track, right? You like to go and just do the calculations and then afterwards think, does that make sense? But do it the slow way first. That way you will never miss a problem. I guarantee it. Okay, so once you do this, you get the number of half-lives because the seconds cross off. So what is this? I don't know. Whatever it is. Say that again? 4.425. And that's with the correct number of 6. Good. That's how many half-lives. So we can take that number and we stick it up over here. That's the number of half-lives. We know the initial amount. That's right here. So now it just becomes plug and chug. We can put this into